All right, well, for our welcome back to Calculus here for our asynchronous day. We are going to take a quick break from the implicit differentiation that we're working on in class and do something that I feel like you definitely could do on your own with a little bit of instruction, and it is definitely related to something that we've done before. So we're going to look at what's called L'Hopital's rule. And it has to do with taking limits. Okay, so let's do some remember, right? Some refresh our memory type thing. All right. If I asked you to take the limit, let's say as x approaches -1 of, I don't know, 2x squared minus 2. Excuse me. Sorry, guys. Over x plus 1. Okay, what would you do? All right, well, I hope that you would start with direct substitution. And we really should get in a habit of checking that before we write anything down. So let's see, -1 squared would be 1. 1 times 2 is 2. 2 minus 2 is 0. So we're going to get 0 on top. We're definitely going to get 0 on the bottom. All right. And so then we have to remember, well, what else? How else do we know how to take limits? Well, one of the first techniques to try is to see if we can factor anything. So let's take a look at 2x squared minus 2. I can take out a 2. Ooh, and then I have a dots. All right, so I know I'm going to be able to cross out an x plus 1. So then I'll be able to take the limit of what's left, which if I cross out an x plus 1, I'm going to have 2 times, oh, sorry, I'm just going to have 2 times x minus 1. I won't even have a bottom anymore. Now, of course, if you feel the need, if you need to put it all together before you do that, please feel free. All right, so our x plus 1 is going to cancel, leaving us to now take the limit of 2 times x minus 1, and that gives us 2 times -2, which is -4. Okay? Nope, did I do something wrong? Oh no, I just wrote it wrong on my paper. Getting pretty good at that lately. Shame on me. All right, let's do another one. What if I asked you to take the limit as x approaches infinity, okay, of something like 3x squared minus 1 over 2x squared plus 1. All right, well, remember when you take a limit as x approaches infinity, and technically you're supposed to start with direct substitution, but that's just going to give you infinity over infinity. And so remember, when you take the limit as x approaches infinity, the process is different than trying to factor or anything. You're really dividing each term, right, by the highest power of x from the denominator, and then simplifying those to see what you have the limit left over to take. So we have 3 minus 1 over x squared, and on the bottom we have 2 plus 1 over x squared. And when you take the limit of those 1 over x squares, remember the limit as x approaches infinity of a constant over a power of x is just 0. And so this becomes 3 minus 0 over 2 plus 0, which is 3/2. Okay? All right, let's look at some other limits that we've done before, or at least one more. All right, let's say I want you to take the limit as x approaches 0 of sine of x over x. All right, this actually came up on the test, and I think a couple of people forgot that has its own rule, right? Because direct substitution does give you 0 over 0, and so then you had to remember that we had a rule for that, right? And that limit was 1. All right, but so that's our review. All right, but one thing that we've never taken a look at is, so just because it's notes, okay, and I want you to have plenty to look at. But what about something like the limit as x approaches 0 of I don't know, e to the 2x minus 1 over x, right? Technically, direct substitution there would give you e to the 0, which is 1. 1 minus 1 is 0. So that would also give you 0 over 0. But we can't factor it, and it's not a trig function, and it's not x approaches infinity, so then what do? All right, or what about the limit as x approaches infinity of ln of x over x? Well, direct substitution, natural log of infinity is infinity over infinity, so that's kind of like our other infinity problems. However, if I try to divide by the highest power of x from the denominator, when I do it on the top, I'm just going to get ln of x over x again. And that doesn't reduce. And so then what do? Well, that's where this L'Hopital's rule comes in. Okay, so let's talk about what it's based off of, and then I'm going to show you how to use it. Okay. All right, so since I can't do these, that's what we're going to, we can use this L'Hopital's, he's a French man, I believe. All right, L'Hopital's rule. Okay, oh, so we can use L'Hopital's rule. All right, now again, I just want to take a second and talk about why this rule works, and then I'll show you what the rule is. Okay, so some writing here. All right, this rule is based on the idea that as we zoom in on a specific point, all right, we'll call it x equals a. Okay, well, remember let me keep going and then I'll relate it to something we've talked about before. Okay, so this rule is based on the idea that as we zoom in on a specific point, differentiable functions, remember that means they're continuous, right? Differentiable functions become locally linear. Okay, now we have talked about that before. Remember, we did an exploration once where I had you start with a curve and then we zoomed in on the same point over and over and over again, and it eventually started to look like a line. That's what I mean by become locally linear. Okay, and when you do that, that function can then be approximated, right, by the tangent line to the function at that point. Okay, we've actually seen that before. Again, what I'm talking about is if you take a graph and you zoom in over and over and over again on the same point, it starts to look like a line. So then we can approximate that graph, right, that particular function by the tangent line at that point. All right, so then what does that have to do with calculus? All right, but remember, right, but tangent lines, well, let's say that, let me go back, but slopes, right, slopes of tangent lines right, equal derivatives, yes? All right, so you'll see where I'm going here in just a second. All right, so if we can approximate a function near x equals a, using a tangent line, then we can use that tangent line to approximate limits as well. Okay, so what I'm saying here is we're going to be able to take the limit of functions like the one with the E in it and the one with the L in it, and other things that don't necessarily factor, or we could even do it with things that do factor. We're going to be able to take the limit of those by approximating the limit using the tangent line. And tangent lines are related to derivatives. All right, so it's all getting ready to come together here in just a second. All right, so let me tell you what L'Hopital's rule officially says. You know, like sometimes when we do theorems, I say, okay, here's the official theorem, but then what does it mean? All right, so here is L'Hopital's rule by definition. All right, it says to let F and G be differentiable functions on an open interval from A to B containing C, except possibly at C. Itself. So that means it has to be a differentiable function everywhere except maybe the exact point C. All right? Assume g of x does not equal 0 for all x in that open interval except possibly at C. All right, and given that criteria, if the limit as x approaches C of f of x divided by g of x equals some indeterminate form like 0 over 0 or some sort of positive infinity or negative infinity over another infinity. All right, so if the limit as x approaches C of that f of x divided by g of x equals 0 over 0 or some sort of infinity, all right, that's what we call indeterminate forms, all right, then that limit can be found by taking the limit of the derivative of f of x divided by the derivative of g of x. Okay? All right, so again, what does this have to do with anything? Like, why can we say that one limit equals the limit of its derivative? Well, that goes back to the whole idea of local linearity. If I zoom in on a function, I can approximate the limit of the top function at this point, right, by using the tangent line at that point. And then I can do, and remember with limits, you take the limit of the top and the bottom separately. And so I can do the same thing for the bottom function, and then I can take the limit using their derivatives, and it will be equivalent to the limit of the original, okay? So that is what L'Hopital's rule says. Now, there is a certain way that you have to actually show your work for L'Hopital's rule. All right, so in terms of like directions for like what you would be doing, all right, you would be finding limits, right? Find the limit. That's really what the direction, that's it. Find the limit, that's what you're doing, all right? But you want to use L'Hopital's rule if necessary. Now, if you understand like when you can use it and when you can't use it, you can actually use it for all limits. So some of you missed some limits on the test, and if those come up again, you will probably be able to use L'Hopital's rule and get those right next time. All right, so let's look at the problems I talked about on the front that we couldn't do yet. All right, so we have the limit as x approaches 0 of e to the 2x minus 1 over x. All right, now remember you still start with direct substitution, but if you're going to be able to apply L'Hopital's rule, all right, because this does come up every now and then on the AP exam in the free response section, and you have to make sure that you show the work appropriately. All right, so maybe in your head you direct substitute, all right, and because you get 0 over 0, this is how you need to show it. All right, you need to show that the limit as x approaches just the top equals 0. And actually, I might even take the time to show the direct substitution there just so you guys can see what I'm doing. All right, so that would be e to the 0 minus 1, which is 1 minus 1, which is 0. And then I'm going to take the time to show that the limit of the bottom function also equals 0. All right, and so because both of those equal 0, we would say, and 0 over 0 is indeterminate. Whoops, sloppy. L'Hopital's rule applies, can be applied. All right, L'Hopital's rule can be applied. All right, and so to get full credit for using L'Hopital's rule on, like, say, the AP exam, you would have to say all of that, and you have to show that the top equals 0 separate from the bottom, because the one thing they don't want to see is equals 0 over 0. All right, so now we're going to apply L'Hopital's rule. And all that means, okay, is that you're going to take the derivative of the top. All right, so let's see. When I take the derivative of an exponential function, I get the exponential function again, but then I need the chain rule, which means I need to multiply by the derivative of the top, of the exponent, and then derivative minus 1 is 0, and then the derivative of the bottom is 1. Notice I did not use the quotient rule. That's not this, okay? We're literally taking the derivative of the top separate from the derivative of the bottom. And now we can try to take the limit again. And I already know I'm not going to get divided by 0, so I can put my equals, I can plug in my 0 for x, and I can get my answer. All right, so what that is saying is that the original limit question they asked me, I now know is equal to 2. Okay? All right, let's try another one. All right, so let's do the other one I showed you at the beginning. All right, ln of x over x. Okay. So again, you can think of it before you write anything down. All right, if I plug in infinity, ln of infinity is infinity, and of course I get infinity on the bottom. So I want to show that the limit, whoops, getting sloppy again, sorry. I need to show them separately before I can use L'Hopital's rule. So the limit as x approaches infinity of ln of x equals infinity. And here's another way you could do it, which equals the limit as x approaches infinity of x. So I'm just showing you that they both equal infinity. And then we would say something like an infinity over infinity is indeterminate. So L'Hopital's rule applies. And then I can apply it. All right? Which means I'm going to take the limit, but now I need to take the derivative of the top function and the derivative of the bottom function. And then 1 over x divided by 1 is 1 over x. And then I can plug in, use my direct substitution. But what you have to remember now is that when you take the limit as x approaches infinity of a constant over x, it always equals 0, but that's because 1 divided by a gigantic number is so tiny we can approximate, or we can say that it goes to 0. All right. Let's see. That's a lot on one page. Let me go to another page. All right. And so then I've just got a couple more examples for us. All right. Let's say I want the limit as x approaches negative infinity of x squared over e to the negative x. All right. Well, all right. I'm kind of thinking out loud, or I'm thinking to myself, let's see, the limit as x approaches negative infinity, if I square that, I get positive infinity. And then, okay, now I got to remember this. All right, so negative of negative infinity is positive infinity, and e to the infinity is infinity. So you do have to know these things. And then, of course, and infinity over infinity is indeterminate. Oh, I can't even, what am I doing there? Not independent, indeterminate. So L'Hopital's rule applies. All right, and so then I'm actually going to apply it. So I get the limit as x approaches negative infinity, and I take my derivative, 2x, and then e to the negative x times the negative. All right, well then I think, okay, let's direct substitute into that. The problem with that is I'm going to get, I'm going to get negative infinity over negative infinity. So again, I need to somehow show that I'm only plugging it into the top and the bottom separately. I'm not actually showing equals negative infinity over negative infinity. But I'm showing that they both equal negative infinity. And so what we're going to do is we're going to apply L'Hopital's rule again, because I got another indeterminate form. All right, so negative infinity over negative infinity is indeterminate. Okay, so we're going to use L'Hopital's rule again. All right, which is still not a quotient rule. We take the derivative of the top, separate from the derivative of the bottom, and 2 negatives make a positive here. And now direct substitution gives me 2 over infinity, which is not indeterminate, but I do need to remember that that is 0. Okay? All right, and then I got one more for us. So you can keep using L'Hopital's rule over and over and over again if you keep getting one of those indeterminate forms. But as soon as you don't get 0 over 0 or some sort of infinity over infinity, you must stop using L'Hopital's rule, and either you're able to find the limit or you have to go back to some sort of former method of finding limits, which doesn't happen very often. Okay? All right, so why don't you pause the video and try this one, okay? Why don't you pause the video and try this one? All right, so hopefully you paused it and you're coming back to me, and we're going to work through this, okay? So let's take the limit of the top, and I'm like, I can already tell, right? Sine of 0 is 0, so I'm going to get lots of zeros. So the limit of the top, well, 2 times sine of 0 is 0, minus sine of 0 is 0. And the limit of the bottom is also 0 minus 0. All right, so L'Hopital's rule applies. Okay, so now we're going to take the limit, but we need some derivatives. So the derivative of 2 sine of x is 2 cosine of x. The derivative of minus sine of 2x is minus cosine of 2x. Then I need the chain rule, which gets an extra 2 in there. And then on the bottom, I get 1 minus cosine of x. All right, well, I'm trying to think. Cosine of 0 is 1. So, I'm going to get 2 minus 2 on top and 1 minus 1 on the bottom. All right, and so I'm going to show that the limit as x approaches 0 of the top equals 0, and the limit as x approaches 0 on the bottom equals 0 again. All right, so L'Hopital's rule applies again. And sometimes you do have to, it takes longer to write it than it does to actually think through it. All right, so then we're going to do it again. So let's see, the derivative of cosine of x is negative sine of x. So we're going to get negative 2 sine of x. And then we're going to get positive, let's see, sine of 2x times another 2. So that's going to make a 4. And then on the bottom, we're going to get sine of x. Well, sine of 0 is still 0, right? That hasn't changed. And so the limit of the top is 0, and the limit of the bottom is 0. So we would get 0 over 0 again. So then L'Hopital's rule applies again. And yes, you keep going if you have to. Now, I'm pretty sure none of the homework problems go this far, but I just wanted you to understand that you might have to keep going and going and going. All right, so let's see. Derivative of the top now would be negative 2 cosine of x. Then we get another cosine of 2x times another 2. And then we have another cosine of x on the bottom. And remember, cosine of 0 is 1. And so we're definitely not going to get 0 on the bottom. So we can actually put equals, let's see, negative 2 times 1 plus 8 times 1 over 1 is 6. Oh, I know that seemed like a lot of work to get to just a simple answer of 6. But if you look back at the original limit, how else could there's really no other way to do it. We don't have enough. We can't split it up into like the trig rules that we learned before because of this subtraction on the bottom. And so L'Hopital's rule was the only way that we could get to an answer on this limit. All right, and so that concludes our lesson for our asynchronous day. There is a small homework assignment in Delta Math. Homework Delta Math. Look for L'Hopital's rule practice, okay? And that will be due on Friday, when we by class time on Friday. Okay?